Hello everyone. In this session, let's try to understand the different forms of correlation and causality between the various variables. So we will talk about different ways in which the relationship between the various variables can be computed and how do we really interpret the relationship between the various variables. We will try to do this from the perspective of uh, the practical usage. So what we will do is we will take one data set, right? The data set that I am using here is from the stock markets, though you can very well apply all these concepts to the domain of your choice. You can use these concepts in marketing, you can use these concepts in HR, you can use these concepts in operations, so you can use them in pharma, you can use them in supply chain, wherever you want. So here my focus is to give you the business context of where do you need to use correlation and causality, and once you use, in what cases, what kind of tests you need to perform on regarding to correlation and causality, and how do you perform those tests in R, what are the various packages and what are the various functions that R is giving to you to execute these kind of tests, and once the test is executed, how do you really interpret the result of that test? So that is what is the major objective. So just for a data set purpose, I am taking the data from the stock markets. Here, for different kinds of sectors, I have taken the monthly returns on the various sectoral indices. So like automobile index on the Bombay Stock Exchange or banking index on the Bombay Stock Exchange. What is the kind of monthly return on each of these? So that's the major thing that I have taken up. That's the data set that I have taken, and we would be running different kinds of correlation related aspects by creating a few questions on that data set and trying to solve and interpret the same. So the data that I have is right from 2007 January or February related returns to 2016 December. So we have almost a 10-year kind of a data with respect to the returns. So based on them, we are trying to highlight and identify different kinds of correlation related aspects on that data, right? So let's get started trying to understand. So we are talking about all these different kinds of tests. So I'll create situations for each of these tests on that data set, and based on that we can execute the same. So initially we will talk about the Pearson's product moment correlation coefficient, which we generally use the default correlation as a function per se. So whenever we are referring to the correlation in a very general parlance, we are actually referring to this Pearson's product moment correlation coefficient. So we'll try to understand how we make the interpretation. So here my focus is not on the formulas aspect. Let me tell you once again. So the mathematics, the formulas, all those things I am not covering in this session. It is purely from a practical perspective. Now I have a data set with me. On this data set, when do I really need to think of finding each one of them? What should be my objective, right? Based on the objective, for what kind of objective, what kind of test need to be performed, and once I know that this particular test is appropriate for this kind of a data, this kind of an objective, Then we are directly going ahead implementing the same in R, and once R gives me a result, I'm using that result for the interpretation purpose. So that's the way this session will go on. If you are looking for the mathematics and the formulas, I suggest that you need to refer to the other books or a few other videos of mine which contain the conceptual aspects of with majority of these topics. Now coming to the other things that we are going to look at, one is the Spearman's rank correlation coefficient. Then we talk about Kendall Tau correlation coefficient, right? So these are the three different kinds of correlation coefficients that we come across. So we are trying to identify how to make interpretation based on each one and when do we use each of these different kinds of correlation. Then if I really want to test between two different correlations, are they really more or less equal or do they differ significantly? Then we are performing some kind of test between two independent correlations. And if there are some overlapping correlation coefficients, I'll give you an example when I go there. Right? I want to find out the correlation between X and Y. Along with that, I also want to find the relationship between X and Z. So in that case, I am referring to an overlapping correlation coefficient. So I want to really find whether X is heavily influencing Y or is it heavily influencing Z, or more or less are they influencing equally. Similarly, I can talk about non-overlapping but dependent. So probably X versus Y, Z versus W. But again, these are not independent. X and Z are not independent. There might be some relationship between X and Z. Similarly, there could be a relationship between Y and W also. But I am more interested in seeing between this group and this group, is the correlation significantly different or are they more or less similar? Then, in the context of correlation, another important test that we look at, generally we use this as a part of factor analysis. Whenever we are doing factor analysis, this test becomes one of the most essential ones, the Bartlett test of sphericity. So I'm going to talk about this and how do I interpret the data using this test. Then, if I'm talking about two different matrices, in the context of correlation, we are talking about correlation matrices between two different groups of data, two different pairs of two different sets of data. And I want to compare one-on-one pairwise correlations across the two sets. In that case, we are talking about the equality of the matrices, for which I am using the Genrich test. So we will try to use that Genrich test and make the interpretations accordingly. Then the last three are more and more associated with the time series, where my data is more and more of a time related data. Right, we will be talking about all of these. So Granger causality test is one important test that we will engage on the time series related data to test the influence of one variable on the other variable across time. Then similarly we are talking about Durbin-Watson autocorrelation test, whether the autocorrelation is primarily correlation with some lag. So whether this autocorrelation exists between the variable or not. So we are looking at two different forms of autocorrelation test, one being the Durbin-Watson test for autocorrelation and the other one being Brosh-Godfrey test for autocorrelation. So these are all the aspects that we can look at in a data set, especially if the data set is a time series based data set. I can think of executing all these tests by creating various instances or various queries on the data set and trying to address all the queries. So from that perspective, this is the data that I am taking. I am just loading that data from my system. So I'm taken that BSC index returns.csv. That's the file, that's the data file that contains the return, monthly returns information. So if I have to quickly look at the dimensions of this, this is dim of this saying 119 rows are there and 12 columns are there in this data. And if I want to look at the first few, right, the first few instances I have taken head of index returns. So you could see that telecom, reality, public sector, oil and gas, IT. So there are different kinds of sectors and their monthly returns per each of these months is typically computed and presented out here, right? And if I'm looking at the structure of this right now, yeah, this is actually not a time series because the months are not being shown as date, rather they are being shown as factors. But for time being, I'm keeping it as it is, but as time progresses, I would like to look at it later, right? I will try to look at it later, wherein if required, I will convert it into a time series data type and would be using some of the tests. But for time being, let me keep it as it is itself. All others, which are the monthly returns on each of these sectors, is a numerical variable with different values in each of the periods. Now comes the tests. On this data, I want to create queries and I want to get into the various kinds of tests relating to the correlation. Here comes the first one, Pearson's product movement correlation coefficient. So correlation is the strength of relationship, as I have highlighted earlier itself, right? Strength of relationship between the variables. That is what we are defining and describing the correlation as. So here my objective is to test, is the product movement correlation coefficient between two variables significantly different from zero? So it means that in this context, if I have to write, are the monthly returns, right, are the monthly returns between each of the sectors, I can take two at a time, but I can take all the pairs at a time as well. Are the monthly returns between each of the sectors significantly correlated, or are they completely independent? That's the kind of question. So which means, is it like the returns of telecom and returns of reality have some kind of a relation between them, right? Either positive or negative or whatever, strong, weak, whatever. Or are they completely independent? Means it might so happen that if telecom has gone up in a particular month, anything could have happened with the reality. Means they are not related at all. But if they are very strongly positively related, it means that if telecom has gone up, there's a good chance that reality also will go up and vice versa. But if there is a negative relationship, it might happen the other way. If the telecom has gone up during a particular month, the reality will go down during that month. So like this, we have different kinds of definitions of the relationship between the variables. So that is what I want to test out. Is the product movement correlation between the two variables significantly different from zero? So correlation can be any number between -1 to +1. So -1 indicates a strong negative relation, +1 indicates a strong positive relationship. Somewhere close to zero means there is hardly any kind of a strong relationship between the two. So like this, I want to do for all the pairs. Now I have 11 pairs altogether. I mean 11 sectors altogether. So pair wise, if I take, I will get approximately 11C2. So which works out to 66. So 66 pairs is what I am going to get in this context. Now out of this 66 pairs, I want to really look at between which sectors the relationship is very strong and between which two sectors the relationship is much weaker. So that is what is my prime objective. So the null hypothesis for this is I make a null hypothesis saying the correlation between every pair of variable is 0. So this is what I want to test, whether it is 0 or is it different from 0. If it is different from 0, either it could be positive or it could be negative. So some of the important points for the usage of this, I need to have variables to be very much quantitative. I could see that all of these are quantitative variables because their type is numeric, and both the variables are assumed to be paired random sample. Paired random sample means the data is collected at one single point in time itself for all of them. So this is for February 2007 for all of them. So that is what is a pair. So every data is like a pair. Each is approximately normal. I don't know whether it is normal or not right now, but I'm assuming that it is normal. But otherwise, how do you check for normality? You can very well go for a psych package, right? I'll say library psychology. So from this, okay, there is no such package called psych, which means I have to install it. Install.packages psych. Okay. So now if I load this package psych, okay, the package is loaded now. Now I can very well go with the function called describe, and I would like to see the skewness and kurtosis for all the values. So this is where I'm going with the describe. Now what I could see is the skewness and the kurtosis indicate whether the data is close to normal or not. So if my data is close to normal, one quick test, though we can think of statistical tests later, but a quick way of looking at from the data, skewness should be very much close to 0 and kurtosis value also should be very close to 0. If this is the case, then we can talk about the data being approximately normal. Now I could see here the telecom data is having a negative skewness, but reality is very close to 0. PSU is very close to 0. But oil and gas is having a negative skewness. Again, IT is having a slightly negative skewness. Healthcare is having a very high negative skewness. But a few of them are very much close to normal. Finance data is very close to normal, 0.04. FMCG is slightly negative, energy is negative, banking is also very much close to 0. So there are some sectors where skewness is very close to 0. But that's not the case with kurtosis. Almost all the kurtosis values are showing big positives, right? Except for IT, which is which is also on the positive side. But apart from that, all others are showing much higher positives, which means the kurtosis, which is a measure of the extreme values. So the extreme values are much higher compared to that of a normally distributed data. So which means the data is not close to normal. It is slightly away from normal. But still, I am making an assumption that the data is close to normal. and the joint distribution between the two. Individually, if I am looking at these two things I am looking at, then I could also look at the joint distribution between the variables. Now here itself there is a problem that the data is not normal, so I don't need to go ahead and look at the joint distribution, which has to be bivariate normal. But for the time being, let's assume that the data is normal, just for us to understand how we use the Pearson product moment correlation coefficient. And we also talk about the linear relationship existing between the variables. So these are some of the important conditions for using this particular test. Coming to R, we will use this function called core.test from the stats package. So which is there as a part of the default. So let me see what this core.test is going to do for us. Right, so it's a test for association between paired samples. That is what it is doing. It's trying to look out for the association between the paired samples using one of the Pearson's product moment correlation. That is what we are going to look now. Or it will also do Kendall Tau, which is our third method that we are looking at today. Similarly, Spearman's row, this is the second one that we are going to look at, which means all three of them can be looked at in one single go, but there are some small differences between the three, so that's where we will be using the same function for all three of them, but with small differences between the two. Okay, now the correlation test, core dot test, I am to give X, I have to give Y. This is one way. Or if I wanted for a big set of values, now I have 11 groups of values. So in this case, I don't need to specify explicitly X and Y. I'll simply say X. Here the X is my entire data frame containing the numbers, numerical column. Then a few more things that I can add to it, alternatives, two-sided, less, greater. So what should be my alternative? There are three types of alternatives that are specified here. When I say two-sided, it means I am trying to compare the correlation with R equal to 0 versus correlation R not equal to 0. When I want to do this kind of a comparison, we are using a two-sided as the alternative. But if I want to compare correlation R is positive, at least positive, versus it is less than 0, negatively related. In that case, I am putting alternative is less. Whereas if I am trying to compare correlation of R less than or equal to 0 versus R greater than 0, then I would specify my alternative as greater. So these two are one tail test because I'm more interested in only one side. So I'm not bothered about whether it is greater than or equal to 0. I'm only interested in is it negative. Similarly here I am interested only if it is positive or not negative. Whatever is at 0, whatever it is, I am not bothered. So only one direction I am bothered. Whereas in this test I am more looking at is it 0 or is it not 0. It could be positive or negative. So that's how I have to choose the appropriate test. That's one input. The method is what differentiates the three kinds of tests. So when I am giving Pearson, it is the Pearson product moment correlation. When I give Kendall, it will become the Kendall Tau, and when I give Spearman, it will become the Spearman's rank correlation coefficient. And I could also give a confidence level, some 95%, which will compute the 95% confidence interval for the correlation coefficient value. Right? It will give me an interval. So rather than saying correlation is 0.5, it will say it could be anywhere between 0.3 to 0.7. So that kind of a confidence interval is what it is going to give for me when I am specifying the confidence level. So probably with this as an input, I think we should be able to execute the correlation test. The Pearson's autocorrelation test is what we will execute first, right? So let me just copy the stuff, core.test. Now X for me is index returns. Then I can also give my alternative, right? For the time being, let me directly give alternative as two-sided, where we are, so which means we would be comparing whether R is equal to 0 or it is not equal to 0. I'm only looking at that perspective. So that is where I'm giving it as two-sided. Then I'm also interested in the method. For now, the method is a Pearson method, right? So I'll give Pearson as the method out here. And I can also give the confidence level, the same 95% confidence interval is what I can get as my output between each of the pairs. So this is what I can very well execute. This one single line will perform the correlations across all the pairs. But of course here, index returns, I'm not interested in all the index returns, right? The first column is a month, which I'm not interested in. So what I can say, take all the rows, I'm taking a subset of index returns. I'm taking all the rows, I'm taking all the columns except the first column. So for that I will ask it to compute the correlation. Alright. But remember here it has made an explicit assumption that each of the variables are normally distributed, which is not the case as we have seen on based on skewness and kurtosis, but here I am assuming that they are normally distributed and their joint distribution is bivariate normal. Based on that assumption, when I am executing this product moment correlation, Pearson's product moment correlation coefficient, argument y is missing. Okay, here numeric vectors of data values x and y must have the same length. Okay, I have to give all of them looks like. It does not take the data frame, so I have to give explicitly. So let me do one thing, let me do for the first one, telecom and reality. So wherein I will take the second column, right? I'll take the second column and I would also consider the third column. Second and third is what I would like to look at for the correlation. So now here the product moment correlation test I can do between only two variables at a time. I don't think I can do it for the whole data frame out here. So this is where it is giving me the Pearson's product moment correlation between index return second column, which is the telecom sector, and the third column, which is the reality sector. Now here I am looking at some important values, right? The T value is 9.64. In this case, a few things to remember, the T value is 9.64, though we will not use this in any way. The most important thing that we are going to use is the P value. The P value is saying it is less than 2.2 into 10 to the power of minus 16. This is a kind of a very least kind of a value. So we can very well assume that P is very close to 0. 2.2 into 10 to the power of minus 16 is more like 16.16 zeros, and after that we have a 2.2, 22 kind of stuff. So which means it's almost equal to 0. So the simple way we will make conclusions at any point is p-value is less than 0.05. So in this case, the null hypothesis for me is correlation is equal to 0, and the alternative hypothesis is correlation not equal to 0. And in this case, because p-value is less than 0.05, we will reject the null hypothesis and will make a decision in favor of alternate hypothesis, saying that the correlation between these two sets of variables is not equal to 0. And when I am looking at the value, it is around 0.665. The correlation between these two pairs is around 0.665, which is close to 1, and it's not anywhere around 0. And even a 95% confidence interval for the same is saying that even if the data changes to whatever sample, there's all possibility that the correlation could be anywhere between 0.551 to 0.755. So it has to lie within this interval itself. 95% I'm confident that whatever is this range that I'm specifying, this will contain the true correlation between those two variables, telecom and reality. So that's how we can test the correlation between the pairs of variables using the core dot test method. Probably quickly, if I want to check out for one more sector, right, reality versus PSU. If I want to see, I'm just substituting 3 and 4 here. Reality versus PSU, if I have to interpret, again there's a completely different, here you see the p-value, it's again 0, so less than 0.05. I will go with, I will have to reject the null hypothesis and I'll have to go with the alternate hypothesis. The alternate hypothesis is saying true correlation is not equal to 0. And when I looked at the value, it is 0.86, which means it is very much positive. And even when I look at the 95% confidence interval for the same, it is somewhere between 0.806 and 0.901. So that's how we are getting the typical computations for the correlation between these two sectors. So that's how we can very well compute, which means in this case the different sectors returns are not independent. There is some strong positive relationship across the various sectors. At least the three sectors that we have tried, we could see that there is a strong correlation across the sectors. Normally when I have to do the simple correlation without the test and all, I could simply use core and I can give the whole input, the whole data frame, especially except the first column, all other columns except the first column, and use core function. So I'm going to get a kind of a correlation matrix in this case, right? I could see that the probably IT and telecom correlation looks much lesser, but with respect to telecom that looks like the least. Similarly, when I look at in all other sectors, I don't see anything lesser. IT and PSU looks still more lesser. But apart from that, I don't see any sectors where the correlations are lesser, which means there are quite a good, and probably in some cases, if you see like banking versus finance, it's almost 0.99. A clear indication of very strong positive relationship between the sectors, right? Okay, so that's how we do the correlation test, especially the Pearson's product movement correlation. But moving on to the next, what if the variables are not normal? So we have seen that the Pearson's product movement correlation coefficient assumes that the variables are normal and their joint distribution is bivariate normal. But in reality, what if the variables are not normally distributed? Now this is where the Spearman's rank correlation as well as Kendall Tau come into picture. Otherwise, everything else is the same. So I want to find out, is the Spearman's rank correlation coefficient between the two variables significantly different from 0? The null hypothesis again is the correlation is equal to 0. Alternate hypothesis, if I am taking it as not equal to 0, then this pair is typically called as a two-sided test, two-tailed test. If I am taking the null hypothesis as correlation greater than or equal to 0 and alternate hypothesis as less than 0, then it is a one-tailed test where I will specify the alternative as less. And if I am taking the null hypothesis as correlation less than or equal to 0 with alternative hypothesis as correlation greater than 0, then I would consider this as a one-tailed test with alternative value as greater. So conditions wise, I am looking at a random sample of ordinal data or a ranked data. So if the data is not in a even if it is in a numeric form, or first of all, if the data is an ordinal or a ranked data, I am not supposed to use the Pearson's correlation coefficient because it is applicable only for quantitative data. So if I have a ranked kind of a data and I want to find out the relationship based on the ranks, not on the absolute values, in that case the Spearman's rank correlation coefficient becomes handy. But if I have to use our same example that we have used earlier, even if it's a quantitative variable, it's not a ranked or ordinal kind of variables, even if they are quantitative variables, but they are far away from being normally distributed, they are nowhere close to being normal. In that case also I can use a Spearman's rank correlation coefficient as long as I assume that the linear relationship exists between the variables, right? So that is where I could use the Spearman, all else remaining the same. I could use the Spearman from the Cordot test, or I could also use the other packages. I'll come back to these other packages. First, let me finish off the Cordot test for all the three. Even we have one more package implementation here for Pearson product movement as well, where we are using correlation test from F basics package. I'll come back to that. So here let me simply do everything the same, right? Cordot test. The only thing is from Pearson, I'll change it to Spearman. So in this case, it is computing the rank correlation, not the product movement correlation coefficient. Now here also, if I look at the Spearman's rank correlation between the reality sector, which is the third column of index returns, and the PSU sector, which is the fourth column of index return, then I am getting the S value is the computation that is done out here. Pearson's rank statistic is what is computed, but what is more important for me is the P value. Again, the P value is 2.2 into 10 to the power of minus 16, which is less than 0.05. Whenever the P value is less than 0.05, we are rejecting the null hypothesis and we are taking our decision in favor of alternate hypothesis. So here our null hypothesis is the correlation is equal to 0. We are rejecting that and we are taking our decision in favor of alternate hypothesis. So I'm making a conclusion that the correlation is not equal to 0. And when I look at the number out here, it is slightly lesser than the number which I have got using Pearson product movement. Here I am getting the number approximately 0.82. For this we will not get the intervals, right? The intervals are more associated with the Pearson product movement itself. In case of Spearman, we are simply getting the overall estimated relationship, strength of relationship between these two variables. We are getting it as 0.82, which is a positive relationship between the reality sector and the PSU sector. So that's how I'm using the Spearman's rank correlation. And the same way I can use the Kendall Tau. Again, for the same, just like the way I have used the Spearman's rank correlation for the data which is ordinal or ranked, or when I am working on a continuous data but it is very much away from being normally distributed, then I can use the Kendall Tau. The only difference again is the method itself. So I can use Spearman's rank correlation as well as the Kendall Tau in cases where the data is an ordinal or a ranked data, or in those cases where though it's a numeric data but the data is very much away from being normally distributed. So when I'm using this Kendall Tau, wow, here the numbers are slightly different, though the p-value is still very close to zero, indicating that I should reject the null hypothesis and go with the alternate hypothesis. But I could clearly see the correlation number here is 0.63, much lesser than 0.82 that we have got here and 0.86 that we have got here. So the strength of the relationship is getting challenged when I'm going with the Kendall Tau estimate to some extent. But still, it is very much closer to 1, indicating a strong positive relationship between the variables. So these are the three different kinds of basic correlation tests that I can very well compute. But at the same time, right, I can go back to the other packages. So we will see what comes out in the correlation test function from fbasics package. So let me install the package fbasics. Let me just check. Oh, fbasics is with a capital B. Okay, now let me load this package fbasics. Right, once this package is loaded, so this is you could see here it is loading the time series kind of package, and it is calculating the basic statistics of the financial markets. So from this I have a few things I can very well use, one being the correlation test. So let me just type what it is doing. Correlation test, we'll go for the help for the same. Test if two series are correlated. Right, so that's the kind of thing that it is doing. So I can do the correlation test, I can simply give correlation test and I can give the method in all the case, or I can simply go with Pearson test and I can give X and Y. Kendall test, I give X and Y. Spearman test, I give X and Y. So that's the thing that I can very well look at. So let me simply go ahead with correlation test. Right, I'll go with the correlation test where I have to give X and Y. So X and Y, let me take these two variables itself as X and Y. Right, I'm taking X and Y as the reality returns versus the PSU returns. Then I'm saying method equal to, initially we'll take the Pearson. We have already executed them earlier. So let me take the method equal to Pearson, that's it. So when I'm using this, the correlation test, you could see more or less we get the same kind of a result. right? But it's only a different presentation part. The test result, the parameter degrees of freedom, it is 117, which is 2 less than your sample size, because we are talking about the relationship between two variables. The degrees of freedom will be n minus 2, 2 less than the total paired sample size. 119 is the sample size, 119 paired, 119 rows of data is there, so the degrees of freedom will become n minus 2. We got the correlation estimate as 0.86, and it has given all three. So if it is two-sided, this is what is the p-value, so less than 0, right? So because in two-sided, our null hypothesis is correlation equal to 0, alternate hypothesis is not equal to 0. If alternative is less, the null hypothesis is r greater than or equal to 0, alternate is r less than 0. If alternate is greater, the null hypothesis is r less than or equal to 0 and r greater than 0 is the alternate. So in this case it has given this is the p-value less than 0.05. So the null hypothesis will be rejected. So the alternate hypothesis is this one, r not equal to 0. The same case goes with greater, right? In this case, so again still the alternate, the null hypothesis is rejected. I have to go with the alternate. So it is saying r is greater than 0, right? Whereas in this case, you are getting that the p-value is 1 greater than 0.05. So I cannot reject the null hypothesis. I have to go with the null hypothesis, in which case I am saying r is greater than or equal to 0 itself. It's not less than 0. So the confidence intervals are saying, the two-sided interval is saying it was anywhere between 0.806 and 0.901, whereas the less than interval is saying -1 to 0.8963, and greater than interval is saying, for greater than the interval is saying it's above 0.817. And that is what is being given by the correlation test function of this particular package, F basics package. I can do the Pearson correlation, or I can do a Spearman correlation. Here the only advantage is I don't need to do the test separately for two-tailed, two-sided or one-sided kind of tests, right? You could see here this is the row value that has come out, which is similar to what we have got when we have executed core dot tests as well. And similarly, when I'm finding out for the other one, which is Kendall, the same kind of output I'm getting. The Kendall's tau value, which is the correlation, has come out to 0.6314. And in all the cases, I could see that the p-value is very much close to 0, which is an indication that I should reject the null hypothesis and go with the alternate hypothesis itself. So wherever the p-value is less than 0, I will reject the null hypothesis and take my decision in favor of the alternative hypothesis. Right? So that is what is the F basics package doing with respect to correlation test. Similarly here, for Spearman, I have one more package called Spearman package. So I can very well talk about that. So we are installing the Spearman package, and let's load this Spearman. And here I am more interested in Spearman.test function. So let's look at Spearman.test function. So this function is a modification of the part of the function core.test, which evaluates Spearman's RAM correlation test. That is what we have already looked at. Besides two approximations used in core.test, where we are specifying method equal to Spearman, which are AS89 and the T distribution. This function allows us to use pre-computed null distribution for sample sizes less than or equal to 22. So if the sample is just a small modification over the original one, especially if the sample size is much lesser. So we have to use this exact when the sample size is less than or equal to 22. But if it is more than 22, I can use any of these two other approximations as well. I can use the AS89 or even the T distribution kind of alternatives. So, I mean, approximations. So, otherwise, everything remains the same. So, I can do a Spearman dot test. Just let's quickly test that out. Spearman dot test, wherein I have to give my x and y values. So, I'll give these two things as my x and y values again. Alternatives, okay, here I have to specify the alternative two-sided versus less or greater. So let me specify the two-sided, right, saying it is correlation is equal to 0 versus correlation not equal to 0. And approximation wise, I can take one of these three approximations. So let's see what difference comes when I am taking approximation as exact, which generally we do when the sample size is less than or equal to 22. But quickly let's look at it. Here it is coming out as 0.8213. So here also it has given you a warning message, exact values not available for n greater than 22. So this is only for the sample size less than or equal to 22. The p-value again is 0, very much around 0, which is an indication that I need to reject the null hypothesis and take my decision in favor of alternate hypothesis. So the correlation is not equal to 0, and I could see that the number is somewhere around 0.82, which is very close to 1, indicating that there is a very high positive relationship between the returns of the reality sector as well as the public sector unit sector. Now the same logic, instead of exact, I can also put AS89. I hardly see any kind of big difference. You see the number is one and the same. The interpretation is one and the same. So I don't see any kind of a big difference, but especially when the sample size is less than 22, that is where I prefer using the exact rather than going with AS89 or even the T distribution kind of methods. So even if I go with the T distribution approximation out here, the number hardly changes, right? So you don't find any big difference, but these are all the different kinds. So basically just giving you a different kinds of exposures to different packages and how they have been computed, right? And if you look at the few details about this function, calculation of the exact null distribution of the Spearman's rank correlation statistics is exponentially hard in N. So basically it is going the pre-computed exact distribution for n less than or equal to 22. So that's the major influence of this particular package. So if your sample size is having a very small data, then if you want to do the rank correlation, Spearman's rank correlation, it's better that you can go with the exact approximation rather than going with AS89 or a T distribution based approximation. So that is where you could use this, right? And with respect to Kendall, we have already covered the correlation test itself. I did not specify any other package with respect to the Kendall stuff. So these are the three different kinds of correlations and their corresponding tests that I can perform on the data to really have a good understanding of whether the variables have some kind of relationship existing between them or they hardly carry any kind of relationship between them, right? Now let's move on to our next topic. Now the next test that I am going to talk about here is I want to test the difference between two independent correlations. So here I'm typically looking at two independent correlations. Basically, let's say the correlation between the index, the PSU sector and the reality sector, or probably telecom and reality, and let's say PSU and IT. So I'm looking at the correlation, two independent correlations, significantly different from zero. Or a better way of talking about is between telecom and reality itself. Let's say for the first 50 months versus the next 50 months. I want to find out whether the correlation coefficient is more or less similar or is it significantly different. So I'm finding out correlation 1, but here we are talking about independent correlation. So the groups need to be completely independent groups. So if I say that there could be some kind of relationship between the first month and the 51st month, then I cannot use this. So basically I am talking about two different groups, right? So here I can very well talk about the same telecom versus reality under the assumption that before 2010, I'll talk about the data before 2010 and or 2011 and after 2011. Right, I'm looking at the values which are before 2011, which means 2007 to 2011 and 2011 to 2016. I want to find out whether the correlation which is before 2011 between telecom and reality, if I say it is R1, after 2011 if the relationship between telecom and reality is R2, assuming that this is completely independent from this, I want to find out whether R1 is more or less equal to R2. This is my null hypothesis, where the difference between these two is almost zero. Or I'm saying R1 is not equal to R2, the correlation has typically increased or decreased. So that's the kind of thing that we are testing out here. So we are making a null hypothesis saying that the sample correlation coefficient between two or more independent samples is zero. So the alternate, so which means R1 minus R2 is equal to 0. That is what we are making. But here the R1 and R2 are between two independent samples. There should not be any kind of dependency between them. So time-based dependency, I am assuming that it does not exist between the samples. The alternate hypothesis says no, that is not equal to 0. There is some positive or a negative value. Again, here also we are assuming that the data is bivariate normal. Pairwise, for each of the pairs, the data is normal. But the sample sizes could be very much different. So probably I can look at less than or equal to 2010 versus after 2010. So after 2010, the sample size could be much larger than before 2010. So the sample sizes don't matter. But we are typically looking at whether the correlations are more or less similar across the two sets, or is there a significant difference in the correlation between these two pairs. For that we are using paired.r function from the psych package. We have already installed the psych package. So I will use this paired.r. So if you try to look at, test the difference between paired and unpaired correlations. This is a very interesting part. Test the difference between two, either paired or unpaired correlations. Given three variables x, y, z, correlation between xy, is the correlation between xy different than between xz? If y and z are independent, this is a simple t-test. If y and z are independent, this is a simple t-test of the z transformed R's. But if they are dependent, it becomes more and more complicated. So that is what we are doing as a part of this. We are trying to compare between, so when we are going with paired, we are comparing xy, xz, yz. And we are giving the values of n. So I want to really find out using this paired.r, right, whether the variables are significantly different from 0. I will give this input. So let's go with it. So we'll start with paired.r, wherein I'm considering xy, right? I'll say xy, I have to compute the correlations. I have to give the correlations. So first let me compute the correlations. Already I have the correlations as a part of the correlation table. But let me again take the correlations index ret. Okay, index ret. I'll take only all the rows but all the columns except the first column. So this is where I get the correlation, right? But I require pairwise correlations, right? Only before 2010 versus after 2010 kind of stuff. So this is where let me take the correlation, right? The same correlation index returns, but the first one, let me take it as between first 50 rows, whatever it is. So I am taking the correlations of the first 50 rows, and then I am taking the correlation between 51st row to 119th row. So those are the two sets of correlations that I am taking, right? So this is the correlation between the telecom and the reality sector for the first 50 data points. This is the correlation between the telecom and the reality sector from the 51st data to 119. Mean first 4 years approximately the correlation was around 0.77, but after that the correlation between telecom and reality went to 0.46. Now I want to use this paired.r for the comparison purpose, right? So I'm assuming that y and z are independent out here. So when I say paired.r, I say xy equal to 0.77. That's the kind of correlation I'm talking of out here. And I will specify xz. I'll specify xz equal to 0.46. So I want to see whether these two correlations are similar or are they different. Now that I have assumed that they are independent, I will not bring in the relationship between these two data points. That I will take care in my next. My n, which is the number of subjects for the first group, which is 50. N2, which is the number of subjects in the second group if it is not equal, because the sample size is different. Here I have taken from 51 to 119, so overall the N2 size is 69. And I can very well set the two-tailed equal to true, which is the default kind of an assumption. Now if you see what this is doing, what this function is doing, to find the z of the difference between two independent correlations, first convert them into z scores using Fisher's z transformation. and find the Z of the difference between the two correlations. So that is what it is typically doing for us. And these are some of the outputs that it is giving. Anyhow, once I execute it, I get this information. The Z is coming out to 2.71 and probability is 0.01, right? So probability, you are getting the Z value as 2.76, which is the difference between the two independent correlations, and the probability of T or Z is coming out to 0.01, less than 0.05. So I have to reject the null hypothesis. I have to go with the alternate hypothesis. And my alternate hypothesis, here the null hypothesis is the relationship, the correlation between them is more or less equal. But now the p-value has come out to 0.01, which is less than 0.05. So I have to reject the null hypothesis. I'm taking my decision in favor of alternate hypothesis. So saying the correlations are different, which is other way of interpreting as the relationship between telecom and reality has changed over the years. Before, let's say 2010 or up to 2010, the relationship between them was much stronger. But after that, the relationship started becoming weaker between the reality and the telecom segment. But on the other side, let's say, let me track this PSU versus reality. Reality versus PSU, right? So the same example, now what I want to look at is XY. I'll take the number between PSU and reality before or up to 2010, and the other one I will consider PSU and reality after 2010, from 2011 onwards. Now in this case you could see that the probability is coming out to 0.09, greater than 0.05. In this case, I cannot reject the null hypothesis. Though the number is 0.89 here, it looked like it has fallen to 0.80 here, but it's not a significant drop as per this particular test. This drop is not a significant drop in the relationship between the reality sector and the PSU sector, whereas between telecom and reality, the drop is significant. So this is how I can use this particular test for doing the comparisons of the change in the correlation between two independent sets of variables. But of course, here the assumption that has been very clearly made is the samples are independent. First 50 returns are nowhere related to the next 69 returns. There is absolute independence between those numbers. They are nowhere related. So that's what is the assumption behind this particular test. So we need to be very clear. Generally what people do is the relationship between two variables, they want to compare, okay, is it similar across the gender? Is the relationship between two variables, let's say income and expenditure, similar between males and females? In that case, I can very well look at the difference between the independent correlations. Here I have used the time period as the bifurcation. Not necessary that the time period would make the variables completely independent, right? So this is one test that we can very well perform, understanding the associations between the variables. Then in some cases I may have overlapping correlation coefficients. So I want to see X, Y, Z. Is X influencing Y? Is the relationship between X and Y stronger, or is the relationship between X and Z stronger? But I know that there is some kind of relationship between Y and Z as well. So by considering that relationship between Y and Z also as an additional variable, in the earlier case we have considered that relationship as constant. But now I want to look at the relationship by considering between y and z, the kind of relationship that is existing between y and z. I want to see whether x is strongly related to y or x is strongly related to z. So that's the thing that we are looking at. So for the question, I want to say, is the telecom sector or is the reality sector strongly correlated with the telecom sector, or is it strongly correlated with the PSU sector? So this is what I want to understand. Reality versus telecom, reality versus PSU. So is the difference between these two correlations, the correlation between reality and telecom minus the correlation between the reality and PSU, is it more or less equal to 0? Considering the kind of correlation that is existing between the telecom as well as the PSU sector. So is this difference anywhere significantly different from 0, or are they more or less equal? So the null hypothesis becomes the difference in the correlations between the reality and the telecom sector correlations versus the reality and the PSU sector correlation is 0. Alternative says no, it is not equal to 0, it is a significantly positive or significantly negative. So the null hypothesis is saying the correlation between one pair of variables, reality sector, to that of the second overlapping pair is 0. This is the overlapping pair of variables that I am looking at. So here also we are assuming that the data is normally distributed. It now considers the correlation between the telecom and the PSU sector also when it is giving the result. So I can still go ahead using the same paired.r that we have used earlier. But if you remember here, there we have used xy and xz, but we did not bring in yz. But now we have to bring in the yz as well. So here I will take these three sectors directly, right? And this is what we can overall test it out. So let me again use the paired.r this time, wherein I will take the whole data, why only first 50 and all. I'll take the complete data. So reality versus telecom. So I'll take xy as this one. This is reality.telecom. Then I have to take xz as reality versus PSU. Reality versus PSU is this one. Then I have my YZ also, wherein I am taking telecom versus PSU, which is worked out to this much, telecom versus PSU. So this is what is YZ. And apart from that, the other information that I have to give, N is the total sample, which is 119. That's my total sample. Now there is no N2 in this process. The two-tailed is coming out to be true. So with this, if I am executing this paired.xy, the probability is coming out to be 0 altogether. So probability is 0 means the null hypothesis is getting rejected. I am taking my decision in favor of alternate. So here you could see that the null hypothesis is these two are more or less the same. The correlation between these two pairs is more or less the same, considering the shared variable reality. But considering the kind of correlation that is existing between telecom and PSU also, it came out that the correlation, the difference in the correlations is significant, which is an indication that both of them are not equal. The correlation between reality and telecom versus the correlation between reality and PSU is not equal. Reality is more related, more closely related to PSU compared to, because it's a negative value out here. Because of this negative, it is more correlated with the second one. So reality is more positive, more heavily correlated with PSU compared to that of telecom. The relationship between the two are not equal. So that's one more kind of a test that we can very well use. But for the same aspect, we have comp overlap correlation package, right? Comp overlap CORR package, and within that we again have the same function for executing similar kind of a requirement. So let's see what it does for us. Comp overlap corp. It's a very simple package, not too many features as a part of this package. Okay, looks like the package is not available now. Okay, the package is not available, so let's take this out, right? At least we are able to do it from the paired.r function from the psych package, so we can go ahead using the paired function from the psych package itself and associate or understand the relationship between the three variables, keeping the third one as constant, keeping trying to understand the relationship between xy and xz by taking into consideration the internal relationship that can exist between y and z, right? Now, moving on to the next, where I want to find the difference between the non-overlapping dependent correlation coefficients. So the words are very clear, non-overlapping, but they are dependent. The earlier case, if you remember, we looked at between 1 to 50 and 51 to 119, the telecom versus the reality sector. So this is non-overlapping, but they are dependent. I have assumed independence between the two for executing it earlier, but in reality, they are dependent, right? So whenever they are dependent, so which means the returns of the first month may be dependent on the returns of the 51st month. So when they are dependent, it's better to go with this particular function. In that case, it's always better that I go with exactly the same size. So I look at 51 to 100, 1 to 50, wherein I'm seeing there is some level of dependency between 1 and 51, 2 and 52, 3 and 53, something like that. So when I assume that they are independent, I could have directly gone with the paired.r which I have used earlier. But if I sense some kind of a dependency between those variables, it's not advised to go with that pair.r. So rather than that, I am using the r.test from the same site package. So here we are talking about two non-overlapping, but we are talking about the dependent sets of data. And I want to see now whether the correlation between the telecom and the reality sectors in the first 50 months is same as the correlation between the telecom and the reality sector in the next 50 months. So this is what generally used to compare the correlation between the two variables. I'm doing the comparison of the correlation between the returns of the telecom sector and the reality sector at two different points in time. The first 50 months versus the next 50 months. And the null hypothesis says they are equal. So the difference between those two is 0, whereas the alternate hypothesis says no, it's not 0, it's either positive or negative. Then if the p-value comes less than 0.05, I'll take my decision in favor of alternate. If it comes greater than 0.05, my decision would be in favor of null hypothesis. Again, this also assumes that the data is normally distributed. We will be using the r.test function from the site package. If I have to clearly look at this and just differentiate, it's just testing the significance of a single correlation, or it also tests the difference between two independent correlations, or it also tests the difference between two dependent correlations sharing one variable, which is the earlier case, or it also tests the difference between the two independent correlations with different variables. All kinds of tests are typically performed. So either it tests the significance for a single correlation, or it could be the difference between the two independent correlations and difference between two dependent correlations sharing one variable, in which case it is called Williams test, or the difference between two dependent correlations with different variables, which is called as Steger test. In all the cases, if you see, these are the inputs that I have to give. N, which is the sample size, right? And if my sample size is different, I have to give N2, but N2 is more applicable if we are talking of independent stuff. But here we are trying to look at the dependent variable, so which means I have to give N12, R12, R34, R23, R13, R14, R24. All of them I have to give, right? Now, the point that we are bringing in here is, if I am looking at first 50 versus the next 50, let me bring both of them here. Core, index, ret. I am looking at first 50 rows, all columns except the first column. Or probably let me take specifically telecom and reality. So which means I am taking the second and the third column, telecom and reality. That's it. I'm finding out the correlation for the first 50 rows. Right, I'm finding the correlation for the first 50 rows where it is 0.772. Then the next 50 rows, which is from 51 to 100. The next 50 rows, I'm trying to find out the relationship between telecom and reality, which is 0.48. And I'm also supposed to find out the correlation pairwise. Right, I am supposed to find out the correlation between all the pairs. Now this becomes R12. So in this case, R12 for me is 0.7722. Then R34, which is the correlation between the next 4 years or next 50 months between telecom and reality. So here I am trying to test whether the relationship between the telecom and the reality sectors have changed over the past few years. So independently I have computed this is what is the correlation. Now I really want to see what is the correlation between 1 and 3, which means the same telecom 4 years back and 4 years later. Similarly, when I do it between 2 and 4, it means the it means the reality 4 years, first 50 months versus the reality sector the next 50 months. And I am also looking at 1/4, correlation between telecom in the first 50 months and reality in the next 50 months. And similarly, I am also computing 2, 3, saying the correlation between the reality sector in the first 50 months and the telecom in the next 50 months. Now, this is where we are talking about they are non-overlapping periods, but they are dependent correlation coefficients. I really want to understand whether there exists that kind of a relationship or not. So let me just try that out. I want to find the correlation between X and Y. The X for me is index rate 1 to 1 to 50 comma 2. That's the one sector that I'm looking at. Sorry, that's one set of values, and the same index rate 51 to 100 comma 2. So indicating the telecom first 50 months versus the next 50 months. I'm trying to find the correlation, which is R13, and this gives me 0.1254, right? Then the same thing I could do with the third column, which gives me R24. So R24 is minus 0.0993. So the relationship between the reality sector returns in the first 50 months versus the reality sector returns in the next 50 months. See here, I'm just comparing whether these two numbers are equal or different. Logically speaking, they are looking like different, but here there might be some kind of relationship between all the pairs. So after considering all these relationships, I want to say whether this relationship is significant or it can be simply ignored. Now I need R14, which means the first 50 I am taking for the telecom sector, the next 50 I am taking for the reality sector. And this correlation is coming out to minus 0.0428, and the final one is coming out to, here I am taking the telecom sector, here I am taking the reality sector. In this case, it's coming out to 0.155. So these are the inputs that I have to give to compare the relationship between the telecom and the reality in the first 50 months versus the relationship between the telecom and the reality in the next 50 months. So we'll use the R dot test now. So R dot test, I have to specify my n values. The n value here is 119. Sorry, the n is 50. We have taken the 50 across. Then R12, R12 is coming out to 0.77, this one. R34 is working out to this being the number. These are the two that will get compared. But apart from that, I have R13, which has worked out to this number. I have R24, which worked out to this one. Then I have R14, which worked out to this much, and R23 worked out to this one. So I have all the pairs of correlations. Though I want to compare between R12 and R34, these are the other inputs that I am giving, and two-tailed is true. So in this case, if I am testing out, I'm getting, if I'm looking at out here, so this is what is the test that I have performed, test of difference between two dependent correlations. gives that Z value is 2.4 and probability is 0.02. So the P value has come out to 0.02, which is less than 0.05. So my decision would be in favor of alternate hypothesis. The alternate hypothesis says no, these two correlations are not equal. Means the correlation between the telecom and the reality sector in the first 50 months is not the same as the correlation between the telecom and the reality sector in the next 50 months. Means the relationships between the telecom and the reality sector has changed over time. Initially it was much, and if you look at the Z value, it's not a negative value, it's a positive value indicating the first period is higher compared to the second period. If I get a negative value for Z, then I could have taken the decision in the other direction, but because it's positive, I say that the first period's correlation value is higher than the second period's correlation value. So this is one more important test that people do, where they are looking at comparing the correlations which are dependent but for a non-overlapping kind of periods. So one more important test that we need to be comfortable with when we are trying to assess the relationships between the variables. The next important aspect of correlation that we are looking at here is the Bartlett test of sphericity, which is primarily used in the context of factor analysis. The major thing that we are trying to test here, this test is more appropriate to all correlation, not just one pair, two pairs. So in given this data, we have 11 different sectors, right? I am looking at pairwise correlation for all the 11 sectors. And finally, this is saying, is the correlation matrix an identity matrix? So basically it is like, what is an identity matrix? I have something like this. All are zeros, only the diagonal is 1. It's a square matrix. So this kind of a matrix is what we are calling as identity matrix. Now, this test typically is trying to find out whether the correlation between the various variables that we are considering is an identity matrix or not. So if it is something like this, it is identity. In some cases, it may be very close to this. In some cases, it may be very much away from this. So that is what is the test doing. So the initial correlations that we have. So in this case, we have showcased. So these are the correlations. So if I look at the whole data, the correlation between the index returns, wherein I am considering all the rows, all columns except the first column. So this is my correlation matrix, right? Now this particular correlation matrix, I want to know whether it is equal to 1 or not. So the diagonals are anyhow 1, but these are not zeros. So it will have to do a test saying, are these very much close to 0 or not. So that is what we are trying to look at in case of the Bartlett test of sphericity. So in all the factor analysis studies, we are going to use them, because if you remember, the null hypothesis is, it says that the correlation matrix is an identity matrix. So there is no need of any kind of factor analysis on the data, and there is no question of dimension reduction in the data. Dimension reduction cannot be done on the data because there is no amount of correlation that is existing between the variables. All of them are very, very close to 0. Between all the pairs, the correlation is close to 0. So there is no need of any kind of dimension reduction using the factor analysis. So that's where it says the factor analysis is of not much of a use all the 11 sectors need to be taken as independent itself. Whereas if the null hypothesis gets rejected, it means that the correlation is not an identity matrix. So all the non-diagonal correlations are not close to zeros. They are very much significantly different from zeros, which indicates that the factor analysis should be an important aspect to be considered. So that is what we are trying to see out here. The data is assumed to be normally distributed, and coming to the implementation, I am using cortest.bartlett from the psych package. So psych package we have also already loaded. So cortest.bartlett, let's see what it is giving. So propose that this particular, so the Bartlett test, that a correlation matrix is an identity matrix. That's the test it is trying to do. So the log determinant, so this is the formula, was distributed as a chi-square if R were an identity matrix. So this would be distributed. So if R is an identity matrix, so this particular thing, the determinant of R multiplied by capital N minus 1 minus 2p plus 5 by 6 was distributed as a chi-square distribution. So that is what is being proposed by Bartlett, and that is what we are doing as a part of a Bartlett test. Now if you see the inputs, the R is the correlation matrix, right? So I have to give the correlation matrix as an input. Then N is talking about the sample size. So we have a sample size of 119. So I have to give a sample size. And the diag equal to true means we'll replace the diagonal of the matrix with 1s to make it as a correlation matrix. If at all it is not 1, so if we have given a variance covariance kind of a matrix, then it would convert them into 1s so that the overall correlation can be, it is more like a correlation matrix. So a very simple input. Let me just try to execute the same on the data so that we can do the testing. The R, which is a correlation matrix. So I'll take this as the correlation matrix. My N, which is the number of observations, is 119. Diagonal, I'll take it as true. So this correlation test has simply computed a chi-square value. That's an intermediate calculation. More important for me is the p-value. So the p-value is clearly telling me out here that there is a significant correlation because I am rejecting, it's less than 0.05, so I am rejecting the null hypothesis. So the null hypothesis of the correlation matrix being an identity matrix is being rejected. So the alternate hypothesis is correlation matrix is not equal to an identity matrix, means the non-diagonals are not zeros, they are significantly different from zeros, which is a clear indication that a factor analysis can very well be performed on this data, and which can very well result in the dimension reduction of the data. That is what is the major objective that comes out through the Bartlett test of sphericity, right? And that's where we will take a call whether we need to do the dimension reduction of the data by performing appropriate factor analysis on it or not, right? Then one more test regarding the matrices itself. I want to look at the equality of two matrices. So here I want to look at the correlation between the sectors, right? I am looking at the correlation between all the 11 sectors in the first 50 months versus the correlation between the same 11 sectors in the next 50 months. So I want to test those correlations. So here it's purely two correlation matrices is what I have to give as an input to see did the correlation drastically change between these two time periods, or more or less they are equal? So this is what is the objective out here. So here my question is, did the correlations across between the sectors, are the correlations between all the 11 sectors similar in the between the first 50 months and the next 50 months as well? Or do you really see some kind of significant differences in the correlations before, let's say, 2011 and from 2011 onwards? So the null hypothesis are saying that the correlations are more or less constant each pair. Now if I have 11, then there are 66 pairs. So piecewise they are more or less constant between all the pairs. Whereas the alternate hypothesis says no, they are significantly different. And here the data is assumed to be independent and normally distributed. And we are using cortest.genrich from the same site package. So if you look at it, cortest.genrich is the name of the function. So chi-square test of whether a single matrix is an identity matrix. I could have very well done the earlier one also here. Or a pair of matrices are really equal or not. So that is what we are trying to do, cortest.genrich, wherein I am giving two different matrices R1 and R2, but look at the description. The sum of the squared elements of the correlation matrix is distributed as a chi-square under the null hypothesis that the values are 0. That's the major thing that he has gone with. From our business perspective, if I have to compare, I am doing a correlation matrix. Two different correlation matrices is what I am giving. If I don't give the second one, by default it would take as an identity matrix. Right, I am giving two different correlation matrices out here, and that's it. I can give the N1 and N2, which are the sample size of N1 and sample size of N2. Right. So let me go ahead with usage of correlation. The Genrich test, cortest.genrich is what I am using. The first thing I would take is the correlation matrix for the first 50 months, and the next thing I'll take the correlation matrix for the next whole period up to the recent 51 to 119. Right, I'll take between these two pairs, means before the first 50 months and after that the next 69 months. So N1 the sample size is 50 and N2 the sample size is 69. And this test is giving only two observations. A probability is saying 1. Probability is greater than 0.05, which is an indication that I cannot reject the null hypothesis. I have to go with the null hypothesis, which says that the correlations are piecewise constant over time. There is not too big difference in the correlations between the sectors across time. If I take all of them into consideration, this correlation is not that significantly varied before 2011 versus from 2011 onwards between these sectors. Right? So that is what is being provided by the Genrich test of equality of the two matrices. Another major application of correlation. Alright. Now, moving on to the next one, where we are talking about the Granger causality test. So it's a very important concept out here. I'm talking about here in terms of time series. Okay, now the correlations that I'm talking of are from the perspective of time series. I'm trying to look at, is one time series useful in forecasting the other? So basically I'm going with respect to time. So I'm considering the data being time based. Now the data is not being looked at as independent, right? The data is being looked at as dependent. So the whole thing is being looked at as a sequence. The first one being February 2007, then it is March 2007. So the data is looked at in an order itself. That is what we are talking of as a time series. So what we are saying is one time series useful in forecasting others? So if we are talking about some kind of a surprise in an independent variable, let's say I am talking about the telecom sector and the reality sector. Some sudden surprise coming in the telecom sector. If it results in an increase in the reality sector, then we say that there is a grander causality that is occurring between the two. In any particular period, if the telecom sector value is increased and which is like a surprise in an independent variable, so it has resulted in a later increase in the dependent variable, then we talk about that relationship being a grander causality. So this month independent variable leading to the next month increase in the dependent variable, then we are trying to bring in the grander causality into picture. And the other way we are saying is, if at all we find that the variables are grander causal, then the past values of the independent variable, so the past values of the telecom sector results should contain the information that will predict the reality sector returns beyond the information contained in the past values of this alone. So not just the past values of this alone. So based on the past values of this, I would be able to predict the future value of the reality sector in case there is a kind of a grander causality that is existing. So basically it's like, if I am able to see that a change in this particular variable later is resulting in an increase or a decrease of values of this particular variable, then we are thinking of, or we are trying to link that these two variables are grander causal relationship exists between them. And if that exists, then I am looking at the past values of this particular telecom returns, saying that this past values of the telecom return should contain the information that predict the reality returns beyond the information that is contained in the past value. So not just using the reality's past values, but by using the telecom sector's past values, I should be able to predict the returns of the reality sector. So that is what is the Granger causality test talking of. And the null hypothesis simply says that there is no grander causality is existing between the variables. But the alternative hypothesis says yes, grander causality exists between the variables, which means I can use one sector's past values to predict the future values of the other sector. So the data are assumed to be independent and normally distributed. So that is one important condition out here. So we are using MSB var package here, and within that we are bringing the Granger.test. So it should be a time series data, right? And what order? So is it just one? So if I say order equal to 1, it means the one past value of the independent variable will influence the dependent variable. If I say order equal to 2, the two past values of the independent variable will influence the dependent variable and so on. So we'll go with MSB var package first to start with. Let me close all these things. So install.packages MSB var. Alright. So I will load this MSB var. So saying library MSB var. So the package is loaded. Now we should be able to see the help for this particular function, which is granger.test, which is clearly talking about bivariate Granger causality testing. For multiple time series, it can perform a Granger causality test between the variables. Now I need to either have it as a time series or as a matrix. That's one important thing that I need to have. So it will give all the bivariate causality tests between the variables. So let me first either convert it into a time series or I can have it as a matrix. So let me convert it into a matrix. So index ret, or probably I'll directly use inside the, and here it is talking about the lag to be used for computing the test. So let's understand this very well. Granger.test. Why it needs to be a matrix? So I'll say as dot matrix, right? I'll have index returns. So I'll take index ret, but I can't take the first column. So I'll take all the rows, all columns except the first column. So for this, I will convert it into a matrix. So that is what is my first input. And my second input P, which talks about the lag to be used for computing. So I'll say P equal to 1. Now for all the pairs, I'm getting this Granger causality. You could see here the F statistic and the P value. Reality to telecom means reality with a 1 period lag is going to influence the telecom, right? So here the F statistic is coming out to be this and the P value is coming out to be 0.54 greater than 0.05. So which means I need not accept the null hypothesis. I am rejecting the null hypothesis, which is clearly saying the past values of reality do not influence the telecom at all. Knowing the past returns of the reality sector, I cannot predict the returns of the telecom sector right now, at least the 1 period older, 1 period lag. And the same way, if you look at almost all of them have a p value greater than 0.05 itself, so there is no way we are able to come to one single conclusion in the whole process. All of them are saying that the 1 month past returns of one sector are not determining, cannot be used to determine the results of, cannot be used to determine the returns of the other sector. All of them have a p value of greater than 0.05, indicating that I have to go with the null hypothesis itself. I cannot reject the null hypothesis. And null hypothesis is saying no such case called Granger causality that is existing between the variables. Mean past values of variable 1 cannot be used to predict the future values of variable 2. So no such kind of Granger causality is existing between the variables for a lag of 1. But I want to see if the same exists for a lag of 2 at least. If I'm looking at for a lag of 2, okay, 0.09 is the number out here. Still not less than 0.05. Finance to PSU, so which means knowing 2 months back returns of the finance sector, I should be able to predict the returns of the PSU sector now. So that's a kind of a relationship, but of course this is not that strong. The same is going with bank versus the PSU as well, with again a slightly slightly above 0.05 kind of a relationship. But yes, this is the information that is very, very significant for us. Knowing the auto returns, 2 months back auto returns, I'm able to compute the returns of the IT sector 2 months later. So the 2 months back returns of the automobile sector are useful for predicting the returns of the IT sector quite heavily. That's one important conclusion that has come out here. So the automobile sector is influencing the IT sector. The past values of the automobile sector are influencing the current returns of the IT sector per se. One important Granger causality relationship that we have seen in the data. Another important one came between the reality and the FMCG sector. 2 months past values of the reality sector are influencing the returns of the FMCG sector as well. Another important relationship that came out in the process, two solid relationships were 2 months old kind of 2 months lag returns. Similarly, now if I consider the 3 months lag, I need to see if something other significant things are cropping out. 0.07, zero point zero 0.07, again another 0.03. So finance is contributing to PSU. 3 months back finance data is playing some kind of role for PSU. 3 months back banking data is playing a role in the PSU, current PSU returns. Two important conclusions again. Right, so some kind of dependencies are very clearly coming out in the process. So 3 months lag, this is what is the story that came out. So probably you could see that some kind of Granger causality is existing in the stock markets. To some extent, again, automobiles 4 months back data is influencing the current banking returns. More significant IT versus banking. Another significant PSU versus banking, especially with 4 months lag kind of stuff. These results are looking very significant. IT is influencing the finance industry, financial sector returns based on the IT returns. Based on the PSU, again the finance returns are being dependent. Based on the banking returns, the healthcare returns are dependent. Based on the finance returns, the healthcare returns are dependent. So we could see quite a good number of relationships, auto and IT again. So these are some of the relationships, finance and PSU again influencing. We could see these are the different kinds of Granger causality relationships that are existing. One sector's previous values influencing the other sector's values. So that is what we could do as a part of the Granger test, causality test, trying to understand one time series useful in forecasting the other. Very, very important test, especially if I have to bring in the past dependencies of one variable into the prediction of the another variable. Right? That is how we are looking at the Granger causality test, which works on the time series data. Now, let's move on to the next test, again with respect to correlation, and this one also within the context of the time series itself. I'm trying to look at the Durbin-Watson autocorrelation that is existing between the variables. Now I'm trying to look at whether the serial correlation or autocorrelation is existing in the sample. When I'm saying autocorrelation, let's say with a lag 1, so it's as good as I'm taking the correlation between, let's say 1 to 50 rows, and I'm taking the correlation between 2 to 51 rows and trying to find the correlation between these two sets of data. This is with a 1 period lag. I want to see whether such kind of autocorrelation is existing in the data. So basically it is like when I am fitting some kind of a linear regression or a multiple linear regression model, considering the period 2 as the dependent variable and period 1 values as the independent variable, or when I am saying lag is 2, period 3 is the dependent variable, period 1 and period 2 are the independent variables. So when I am fitting this kind of a regression model, I get some kind of residual. I am trying to see whether the residuals are more or less independent or not. And that is what is being tested as a part of the Durbin-Watson statistic. The null hypothesis says that the residuals are uncorrelated, means they are independent. There is no, so when they are independent, there is no dependency with respect to the past. So P2 is nowhere dependent on P1. So that's the reason the residuals that has come out are typically independent. So the residuals are very much independent, which is also saying that the no autocorrelation is existing between the data pairs. So here the major assumption that is being done is whatever are the residuals that are coming out from the regression model, they are assumed to be stationary. Stationary means any set of values we take, more or less the means will be similar and the variances also will be equal for any set of values for any particular time period. The variances are equal, the means are equal, and all the statistical properties between any two sets of data will always remain stationary. That is what is the meaning of the stationary process. And they are all normally distributed. The residuals are normally distributed with a mean of 0. So the mean value of the residuals is approximately 0. And this method will not be valid if there are lagged values of the dependent variable on the right hand side of the equation. So we are trying to build a relationship between the dependent variables and the independent variables. But within the independent variables, again, if I have the lagged values of the dependent variable itself, then I should not use the Durbin-Watson statistic. I'll be talking about the next one that I'm going to look at. So this Durbin-Watson statistic is what we are using from the CAR package. We will load the CAR package. It is more like it's an advanced regression mechanism. That is what is CAR package standing for. So I would load the package install.packages. I'm going with a CAR package. So let me install this package also. Right, I have installed the CAR package. Then we have Durbin-Watson test function. Compute the residual autocorrelation. For all of them, it will compute the residual autocorrelation and generalized Durbin-Watson statistic along with their p-values also are typically computed. So that is what I can give. I have to simply give the model, that's it. And the method, there are two different methods. So the Durbin-Watson statistic I can simply give the model. Model means I have to give the dependent variable and the independent variable. And because I am performing the linear regression, I will use the LM function there. So let me just get started with that Durbin-Watson statistic, where I am specifying the model as the linear model, linear regression, which is what we use LM. I take the dependent variable out here. Right, let me take the dependent variable as one of them. So the telecom, let me take the dependent variable I want to try to understand if one is influencing the other. So I will consider index returns. The dependent variable, I'll take it as reality. So I'll take all the rows and the third column, that is what I take as the dependent variable. Tilde, I'll take the independent variable, which is index returns, where I'm taking the second column. I want to see whether the telecom returns are influencing the reality sector returns. So this is where I'm saying the model is a linear model between index returns third column, which is the reality sector, and the index returns second column, which is the telecom sector. And max lag. Okay, so it has to compute the lag. So I will say the max dot lag, instead of one period, sometimes I may be interested in giving up to 2 or 3 periods. So let me just look at for the 3 periods to see if there is some kind of an influence. Right, I'm not doing a simulation, so I don't need to bother about these things. Then I need the method. Again, this method is also for the simulation purpose itself. And alternative is something that I need to give because I'm interested in whether it's a two-side or a one-side kind of stuff. So I can go with two-dot-sided. I think that should be sufficient. Right, the Durbin-Watson test, I'm going with the model as well as this. So if you see here, this is what it is for each of the lags. The autocorrelation is simply computed between these two. Right, the autocorrelation is computed between the dependent variable and the set of independent variables. The autocorrelation is simply computed, and this is a Durbin-Watson statistic. I'm more interested in the p-value because here also the null hypothesis is simply no autocorrelation exists. So the alternate hypothesis definitely becomes the alternate that the correlation between the variables, the autocorrelation exists between the variables. So here we could see that the p-values for all the three lags are showing greater than 0.05, indicating that I need to go with the null hypothesis itself, not the alternate hypothesis. So the null hypothesis is clearly saying that the residuals are uncorrelated and no autocorrelation is existing for any kind of a lag. For each of the lags, there is no autocorrelation that is existing between the variables. So that is how I can use the Durbin-Watson statistic to examine whether there is any kind of a serial correlation or an autocorrelation present in the data sample. The same thing I can execute through Broish-Godfrey autocorrelation test as well. And exactly everything remains the same. The only difference being here, it will not be valid if there are lagged values of the dependent variable as the independent variables. Whereas here I don't mind, even if I have the lagged values of the dependent variable as a part of the independent variable, I can still go ahead with Brush-Godfrey autocorrelation mechanism. So this is where I can simply go with the BG test from the LM test package. So let's install the LM test package. So if you see the BG test, which is Brush-Godfrey test, so let me load it first. So then let me see the BG test, which is now telling me perform the Brush-Godfrey test for higher order serial correlation. So I have to give the formula, the order. everything remaining the same. I have to give the formula, I have to give the order, and that's it. So the formula again is between the dependent and the independent variables. So the order is telling me where I'm going for 1 period lag, 2 period lags, etc. So in this case, if I'm going with the same, right, the formula that I'm going with is, I'll use this. So this is my formula where I'm looking at the index returns third column, the reality sector versus the second column, which is the telecom sector returns. And order again I can set it to 3 so that I can look at the first 1 period lag, 2 period lag, 3 period lags, etc. Here also the same logic. The null hypothesis simply is going for there is no autocorrelation between the variables, which is what is very clear out here as well. The p-value is 0.83 greater than 0.05. Clearly understanding that I cannot reject the null hypothesis, I have to go with the null hypothesis itself. So I cannot reject the null hypothesis. So even from this data, I am able to say that there is no way the past values of the telecom are able to influence the the reality sector returns in any manner. So even the Brush-Godfrey autocorrelation test is confirming the same for me. So these are the different kinds of learnings that we really need to have as far as the correlation between the various variables is concerned, right? The correlation has a lot of association with the causality between the variables as well. So having a good understanding of the overall different types of correlations that we look at between the variables, understanding in what aspect, what kind of correlation we can very well look at, what are the supporting R packages for me to compute those kind of correlation. If I'm able to visualize from that perspective, it gives me lots and lots of helpful things in performing the data analytics successfully. I hope you have got good amount of understanding on all these various aspects of correlation. If you have any further queries, you can very well get in touch with me by giving me a call on the number that I have given below, or you can even send in an email at the email address provided below. Thanks a lot for listening to this session. Thank you very much.